Welcome to week 2 live session on the discussion sessions we do on molecular spectroscopy of physical chemistry perspective, a course offered by NPTEL. I am Orko Provo, PMRA from IIT Bombay Chemistry Department. So I am here to solve some numerical problems with you so that you can get the help to solve the assignment problems and discuss if you have any doubts during the sessions, live sessions, or the your study sessions with Professor Anindya Datta. So I hope you are enjoying the videos till now and you are gaining some knowledge. That is our motto. So our main objective is to give you the solutions of numerical problems and we'll try to solve some weekly assignments and clear the doubts and give you some practice questions to work on. These sessions will be recorded and available on the YouTube for your reference. NPTEL will share these documents with you, the notes, the slides and all. So this is in this slide, as you can see, this is an electromagnetic spectrum. We at the left hand side there is long wavelength, X-ray radio waves and microwaves, and from there we are going to shorter wavelength like gamma rays. As you know, energy varies energy is inversely proportional to the wavelength, as well as the frequency is also inversely proportional, right? So as you can see that energy increases when the wavelength decreases. So the energy of a gamma ray is always higher, right? But for this particular course right now we are going to deal with in this session we are mostly going to talk about these microwaves or microspectroscopy, which is related to rotational motions or rotational spectroscopy. Okay. And before going there, we will look on the previous day's discussion on quantum field calculation. So mainly quantum field, since quantum field can be calculated two ways. Sorry. One is relative quantum field, which we are going to discuss today, and another is absolute quantum. So for absolute quantum field, you will need an integrating sphere and most common usage is the relative method. Why relative? Relative to what? So you need a quantum field standard. What is a quantum field standard? So we call a fluorophore dye a standard, a quantum field standard, when the quantum yield of that standard is not dependent on the excitation wavelength. Okay. So in this particular case, so what I am going to show, this is the relative field quantum calculation formula where we are going to get the sample. This is sample, your pi s is the quantum field of your sample, pi r is the quantum field of your reference, which is standard here, and this is an integrated area of the absorption peak, and this is for the sample and this is for the reference, and this is the absorbance factor, the correction factor that comes into picture, and this is due to solvent. This is the refractive index of the solvent, so which is n. So now if you are using the same solvent for your sample and the reference, then this factor is going to be 1, but if it is different, then you need to choose a different value. Okay, so here in the graphs what you can see is really a data of my experiments, so that is a real problem. So as you can see, this is absorption, this is emission. So as you can see, my compound is R1 and I have taken, so this is my dye, and this is also a dye, but this is I am talking about as quantum field standard or reference. Okay, so as you can see, we need to take a quantum field standard which have a excitation similar to our similar to or same to our absorbance, okay, which have a similar absorbance value, or they have a spectral overlap. So actually the maxima is here 425, but for this case we are going to excite our sample and our reference with 445 nanometer light, and by doing that here we got the C153 emission spectra, and this is our sample emission spectra, as you can see. So what are the things we need to calculate? We need to calculate it. So for your pi R1, what we are going to get actually, we need to have the quantum yield of C153 is known. Okay, that is why this is also standard. Now we cannot take any fluorophore as arbitrary as a quantum, for relative quantum measurement. So we need I of R1, then I of C153, and then we need these values 1 minus 10 to the power minus a. This is not R1, this is for 153. C 153 by 1 minus 10 to the power minus a R1, and I need another factor. Here the factor is, so in case of R1 this is in ethanol, solvents is ethanol, sorry, my mistake. In case of my work, the solvent is cyclohexane, and for these the solvent is ethanol, coumarin in ethanol. So this is N R1 square, or you can say, I can actually write ethanol, right? Sorry, cyclohexane. And this is N square of ethanol. So I'll give you some values here, and we'll calculate some. That is the refractive index. I will check it in the internet. Refractive index of cyclohexane is 1.43. So this term this is 1.43, and the refractive index for ethanol is something around 1.36, I guess. This is 1.36, and this is 0.54. Okay, so quantum yield of A is 0.54, which actually means 54%. Okay, in case of, so let me tell you, so the convention is to use the decimal point in case of the molecules, and when you work with the nanomaterials and all, or when you term it as photoluminescence, that time you call it in percentage. So there is some conventional thing. Usually if we are discussing about the molecules or dyes, we talk it in decimal points like 0.54, which actually is 54%. So now we'll calculate it. So for calculation we'll need these values IR1 and all. So I'll show you how to do that. So I will, so these are the origin files. I'll click on this origin file. I'll show you what are the values as 450 nanometer where we have excited our samples. First we'll check with the absorbance values. Okay. So as you can see the origin file here. This is the plotting software where we have plotted our thing. So at 450, as you can see, for the blue one is the our standard or reference. Blue one has a quantum yield of absorbance of 0.024. Okay. I'll not bother about the other values. And what about the R1? So at 450 has almost similar, right? 0.022. So we'll cut it from here. We'll go back to our presentation file and we'll write the values here. So use a blue pen, right? Blue color. So AC153 was 0.024 and absorbance at lambda excitation is equal to 450 nanometer. And what about R1? 0.022. It is best to keep the values near or similar. So bringing them equal is very different, but we have to make sure they are at least close. Okay, the values. And what we are left with the intensities, right? The integrated intensities. For it also will go to the next curve. Sorry. Here. Okay, another origin file. So for the first one, I will select this. So this is my sample, right? The dye sample R1. So I'll go to analysis. I go to mathematics, and I go to integrate. Okay, integrate manual. I don't need the curve output. I just need the values. So as you can see, whatever values we got, the area of the integration. So area under the curve, which is this. So I'll copy this maybe. I'll write it here in my notebook first and then I'll write it. So this is around 507,444,82.8, which is actually 350744482. 5074 What about our standard? The standard have a intensity here. So I'll go to analysis, I will integrate mathematical area, which is 42248506.4. So there are 442248506.4. Okay. So we'll have this. We'll go to our presentation file and we'll write it here. So I of R1 is whatever we have got, 50744482.8, which is actually 3. If you see this number and this is nothing. What about the reference, that is C153? The area under the spectra is 42248506. Right? So we'll plug these values here and we will see what are the values of R1 we are getting. is 0.54 into 5074482.8 divided by 42248506.4 into, I'll again need to shift this a bit, shift it here, and this is 1 minus 10 to the power minus the absorbance value for common 153. Don't forget the minus sign. 422. We can actually neglect this term as this is equal, you can say. And what is this value? 1.43, 1.43 square and 1.36 square. So I'll use my mobile calculator to get these values. Get it, the values 0.54 into 5074482, I missed 14.8 divided by 42248506.4 into 0.024 by 0.022. This is done into 1.43 square divided by 1.36 square, which is 78, or you can say 0.78. We are getting a quantum yield value 0.78. Okay, so the quantum yield of this, so we write it generally, we use the red color pen. So quantum yield, quantum yield of R1 cyclohexane is 0.78. We write it with respect to C153 in ethanol. You always need to mention when we use a radiative measure, and we should also mention the 5 of C153 is 0.54. Okay, so this is a process by which, so I wanted to show you how to calculate the quantum means to get you, so that you can get a better idea. Okay, now we'll move to our main topic for the week 2 discussion, which is the rotational spectroscopy. So actually today we are going to discuss some of the numerical problems on the rotational spectroscopy. So before doing that, we will discuss the formula and where the formula has come from. So we'll discuss that. So the formulas, before going to the formulas, as you already know, we are mostly going to deal with the in rotational spectroscopy. We have to we will mostly deal with a two body problem. Uh, Two body problem. We'll start from here. Two body problem. That is a non-rigid rotor. Firstly, sorry, we are approximating a rigid rotor. So what is rigid rotor? Rigid rotor, the radius is unchanged, but calculation with a two body problem is problematic. So we will convert it to one body problem by taking the diameter of uh, the radius of this rigid rotor to the radius of the gyromagnetic ratio, and from there on we will try to solve it quantum mechanical, but we will not do the quantum mechanical part here. But let me give you an idea. We are going to mostly deal with the spherical harmonics, like the hydrogen atom. So the spherical harmonics is this is the spherical part of the wave function which depends on the theta and phi, right? So this is the spherical harmonics, and for rigid rotor we will mostly going to deal with two quantum numbers, that is J and capital N. So in hydrogen we used to take it as capital L, small l and uh, small small l and small m. So you know that this is your angular momentum operator, right? So when L square operate on the spherical harmonic, you are going to get some angular momentum value magnitude, and you are going to get back your spherical harmonic back. What is the value for rigid rotor? This is the value, J into J plus 1 H cut square. Okay, so this is your angular momentum. But how angular momentum is related to the energy? We are mostly going to rotational spectroscopy. We want the energy and wavelength, those things. So energy is nothing but, I will take it as another color maybe. You need to divide it with a 2I. I is moment of inertia, and also divide this section. So you are going to get your energy maybe write it with the red pen here. E of J. J is a quantum mechanical operator when J can be, what are the possible values of J? J can be 1, 2, 3, 4, any positive integer. It cannot be 0. Okay, why not 0? You are going to see the energy EJ is, I'm going to discuss it, into J plus 1 h cut square by 2I. J is the rotational quantum number where J can be 1, 2, 3, 4 and so on. Why it can't be 0? Because if it is a 0, then it can be actually 0. It can be actually 0. I am sorry. It can be 0. Rotational can be. Is it 0? Let me check it once. Yes, so rotational quantum number can be it can be 0, 0 to 1 to 3, 4. So I will discuss why it can be 0. So if your rotational quantum number is 0, then what is your energy is going to be? Your energy is going to be very sorry. Your energy is going to be 0. Then you may say if it is 0, then there is no rotational motion, or the particle is fixed, or energy is not there, then it is violating the Heisenberg uncertainty principle. No, actually no, because see here it can be. So the I think it is discussed in the class also. So as you remember, the theta is the angle between so angle the dipole moment is creating from your z axis, right? So it can be from 0 to pi, which is 180 degree, and at x axis xy plane it can be 0 to 2 pi, that is 0 to 360 degree. So when ej is 0, you can't really know where the position is. Energy is 0, but see it can be anywhere, any value of theta, any value of phi, right? So there are infinite number of means the probability is infinity to find out the particle. So actually this is following the uncertainty principle. Even if the energy is 0, the uncertainty is energy is 0, that is why we are finding the probability is also infinity, right? So it is not violating, so j can be 0. So while solving actually the thing, you will get to know more why what can be the possible value of, and the unit is in joules, right? Now most of the time we are going to need it in centimeter inverse, so we will divide ej by hc. So we are going to get j into j plus 1 h cut square 2I. So we'll break it down maybe a little bit. So j into j plus 1. So h square will become h, and this is 8 pi square I c. Okay, I is your moment of inertia. Most of the time I can, and see this is an fundamental constant of a molecule. I'll highlight this part. Sorry. So this is particularly a constant for a molecule. H by 8 pi square IC. This is known as the constant B, which is your rotational constant. energy is V into J plus 1 centimeter inverse. Okay. Okay. Now, what is the difference between, so the energy can be, so what is the energy of J equals to 0? That is 0, right? What is the energy of J equals to 1? If you see, you put 1 into 1, a 1 to 2, that is going to be 2b centimeter inverse. That is energy J equals to 2, that is you are going to find out of 6b. What about J equals to 3? You are going to find out 3 into 4, which is 12. What about J equals to 4? We are going to find it out 20. From here, what I am trying to see, and so this is the typical rotational energies. And if you see the gap between the energies, so this is actually 2b centimeter inverse gap. So here the gap is 4b centimeter inverse. Here the gap is 6b centimeter inverse, and here the gap is 8b centimeter inverse. If you see the gap between each is now 2b, 2b and 2b, and this will go on. So the gap between each transition 0 to 1, you will get a line at 2b. Then from 1 to 2 transition, we are going to get a line at 4b, right? So this is how your rotational spectrum will look like. Suppose I am not considering the intensity value now. Suppose this is your 2b line. Now next transition you are going to get at 4b, then 6b, then so the values you are going to see 4b, 8b. So these are the typical transitions. So this is mostly wave number in centimeter inverse, right? And this is the intensity. I use this side. See, so this is actually for your 0 to 1 transition, right? So here this is for 1 to 2 transition. This is for 2 to 3. This is 3 to 4. So gap is always the 2b. Okay. This is another thing. And how to see the gap from here also? Suppose this is the gap in epsilon. You can write it like this, that energy of J plus 1 state and energy of J, so it is B J plus 1 J plus 2 minus B J plus 1. You can take B J plus 1 as common. Now J plus 2 minus J, so you are going to get 2B J plus 1. So this is your gap, delta E gap. Okay. So when your initial, so when your initial J is 0, then it is 0. When it is the gap, so this is, so I will highlight this. This part is actually referring to these parts, right? And also to these values, what we have missed, right? Okay. Now comes the transition moment integral, and I will not go into the recursion formulas. So to solve to get the transition moment integral, I hope you have seen the videos. So we have a few selection rules or conditions, you can say. I will try to write it with this thing. So it is selection rule for rotational spectroscopy. See, the first condition is someone there in our meeting. Stay. The first condition is your dipole moment should not be zero. So your molecule have to be a polar one. That is, you know, from the when you have solved for the transition moment integral, right? TMI. So your TMI, transition moment integral, which is actually a integration from your, when your, this is suppose your final state, this is your dipole moment, and this is your initial state wave function. This should not be zero. Okay, so this will mostly take place when your delta J is plus minus 1. So this is the selection rule. Okay, and these are some of the conditions, and this is unchanged for whatever direction of z direction or z or y polarization you are using. But this transition for along the z direction, your delta m should be equals to 0, and delta m can be equals to plus minus 1 for mu x or y direction of your transition, but we are not really discussing that here. So what are the useful information from here, or another formula sir has also discussed, that is regarding the population, right? So population of a jth state will depend on the degeneracy of a rotational state, right? Which is 2j plus 1 is the degeneracy of a state. Why j 2j plus 1? Because there are 2j plus 1 number of uh, uh, m values will come, right? 2j, for each j there is 2j plus 1 number of capital M values. So that is a degeneration, and also varies as the population of the Boltzmann constant, you can say, or Boltzmann distribution, which is e to the power minus Ej, this Ej into divided by kBt Boltzmann constant into temperature, right? And when one differentiate this, you will see that J max is going to be root over kBt by 2 rotational constant 2b Hc minus half. You are going to get this. What is usually tells us that for a particular temperature, intensity will be something like this. For a particular one, it will be maximum, and then again it will decrease. It will look something like this. Okay. So suppose at certain temperature, this transition will be more visible. The second the 2 was more populated. That is why more transition is taking place from 2 to 3. Now when you will increase your temperature, so actually as sir has also discussed, these gaps are very low energy gaps. These are easily populated by thermal energy. So when you give some thermal energy in terms of heat or something, thermal energy, so your population of the higher excited state will get high. So you will see a red shift in the spectrum nature. So these are the common formula we are going to use, and if something else is we are going to use, I will discuss. So with this, we will solve a few numerical questions. I guess uh, this will excite you more because the main aim was to solve some numerical questions, right? Okay. So the questions I am going to take, these are from physical chemistry from Atkins and 8th edition, and you may check the book for the 13th chapter number 13, molecular spectroscopy. The first question says that, so first we will deal with the basic question that which of the following molecule may show a pure rotational micro absorption spectrum. So what was the main condition of a micro spectroscopy? That your molecule should be polar. So it should have some dipole moment, right? Hello. So so are you a regular student of this molecular spectroscopy course? So I am a TA of this course. Hi. Can you hear me, Dharani? Hello. Can you hear me? Hello. So we are actually discussing this part, I guess. Oh, I was not shared, but I hope this part is visible maybe. Anyway, we will go back to our discussion. So, the main condition of a molecule to have a pure rotational spectrum is to, so that they can have a dipole moment, and here as you can see, which of the molecule can have a dipole moment. So diatomic homonuclear, are they going to be have dipole moments? No, right? So actually this hydrogen atom, hydrogen molecule, it is not going to show me a rotational spectrum because dipole moment is 0. But HCl is going to show me because it is a polar molecule. Is methane a polar molecule? Methane is not a polar molecule, so it is not going to show me a rotational spectrum because mu is 0. What about chloromethane? It is actually a polar molecule, so it is going to show me spectrum. What about CH2Cl2? It is also polar, right? So it will also show me rotational spectrum. So similar question in the second question, which is which of the following molecules may show a pure rotational microwave absorption spectrum? As you see, water H2O, hydrogen peroxide H2O2, NH3 which is ammonia, N2O which is nitric acid, right? Or nitric acid or nitrous. Is nitrous oxide. Sorry. If you check the polarity of this molecule or the structure, first you try to see the structure, then you try to see the bonds, and from there you will get an idea that if it is going to be a polar or not. If you see, in all of these are polar. Molecules are polar. dipole moment is not equals to 0. So all are microwave active. For this question, this here only hydrogen chloride, chloromethane and dichloromethane are uh, microwave active. Okay, so I will may highlight this so that it won't create any doubt. The trick is try to look at the spectra, try to see the symmetry. I'll write it, point it up. Find the symmetry. This is actually the second point. First point will be draw the structure. If it has any rotation, we'll suppose the point group, with C like CN, CNV, these are rotational active, okay? C sigma V or CD, try to see, huh? Now the next question, calculate the frequency. So we'll start from calculating this, okay? Calculate the frequency of the transition for J 3 to 4. So this is the general convention, how to write this. 3 to 4 transition in the pure rotational spectrum. So we should also write it here also, right? So I think we cannot rewrite this, but okay. So calculate the frequency of the transition J 3 to 4 in the pure rotational spectrum of 14N16O, that is nitrous oxide. Nitrous oxide is N2O, what we just discussed. Uh, Nitric oxide, right? So this is a particular isotopes are there, 14N and 16O. So just see it how to do it. Then so what are the things we'll require? So equilibrium bond length is given, which is R, that is 115 picometer, which is 115 into 10 to the power minus 12 meter. What else is given? It is given that the transition is going from 3 to 4. So what is the energy? So delta E is 2B. What was the formula? J plus 1 centimeter inverse. So here what we have got, 2B J plus 1 equals, do we have? We don't have, but we have the J, the starting, right? So we have 3. So it will be 3 plus 1, 4, 8B centimeter. So we need to calculate the rotational constant B. Which is H 8 pi square C I. And again I will just write it in terms, I will just break I as mu R0 square, right? Mu is the, here mu is not your dipole moment, mu is reduced mass. Did I mention it here as, so I didn't mention it here. So reduced mass, which is so actually your mu is m1 m2 by m1 plus m2. So what is here? As you can see, m1 is, suppose this is uh, 14 into 16 by 14 plus 16. This is atomic mass unit square by atomic mass unit, right? So you are going to deal with 14 into 16 by 30 AMU, and 1 AMU is equal to, we need to be very careful with the unit. 1 AMU is equal to how much kilograms? 1.66 into 10 to the power minus 27 kilograms. So what I am trying to do it here, I am converting all to the SI unit, so that I can, so that it will be easier to calculate. So I will calculate B again here. So what is my B? B is H, I know, Planck constant, right? 6.626 into 10 to the power minus 34 joules second. Then I have 8 into 3.14, square of that, 3.14, square of that. C is, I'll write this actually in centimeter, okay? So I will tell you why I am writing it in centimeter. I could have written in meter, as I told you I am taking the only the SI, but let me first calculate the reduced mass first, which is 14 into 16 divided by 30 into 1.66 into 10 to the power minus 27, which is actually 1.24 into 10 to the power minus 26 kg. So I write it here, 1.24 into 10 to the power minus 26 kg. And what is R0? It is given picometer, but square of that 105 square, and I will take 10 to the minus 24. This is meter square. What is joule? Joule second is actually kg meter square, okay, second inverse. If you, how to do that? Joule is Newton meter, okay. Newton is force. Force is what? Mass into acceleration, right? So mass into acceleration. Then your meter is there. Then second is there. So if you multiply this, so this is actually joule second is, I can write it as, I erase it here, kg meter square second. Oh, why? So this is also second inverse, centimeter and second inverse. So I will cut a few terms. So that is your second inverse gone, then meter square gone, kg gone. So what is there left with? Centimeter inverse. So I will first write this in centimeter inverse, and let me calculate the rest of the thing, okay? So 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 3 divided by 10 to the power 8 divided by 1.24 divided by this 10 to the 26 minus 26 divided by 115 square divided by 10 to the power minus 24. It is going to give me, it is actually giving me 170 centimeter inverse, which is actually odd. I'll recheck my calculation. Okay, I'll redo it. 6.626 divided by, just take these ones. Minus 34 and 10 to the power minus 26, that will become 10 to the power minus 8, 10 to the minus 8, 10 to the minus 8, it will become 10 to the power minus 16, and there it is to the minus 24, it will become 10 to the power 8, 10 to the power 8, you multiply this, you have 10 to the power 2 into 1.7075, which is 170. So actually the B value is coming as 170.75, which is a little odd, but for the time being let us believe that. So this is coming as your B value, right? I hope I have not done any mistake. If I have done any mistake, please try to rectify yourself. And then we have the B value. So the what about the energy? Energy is going to be 8B. So wave number actually is going to be 8 into 170.75 centimeter inverse, and if you want it in frequency, right, so you need to multiply with it c, right, which is the speed of light, is 3 into 10 to the power 8 meter centimeter inverse, and meter centimeter in hertz. So you are going to get something around get something around 4.098 agarose into 11. Okay, so this is what you are going to get. Okay. Okay, so this is the frequency you are going to get, this many hertz. So let me once check if this frequency fall into the electromagnetic spectrum we are discussing, right? So see, electromagnetic spectrum is microwave. They are saying it is somewhere from 10 to the power 8 to 10 to the power 10 hertz, and we got something around 400 to the power minus 11, 10 to the power 11. So that is what I am a little worried about. The B value generally comes as 5 centimeter inverse or 6 centimeter inverse, something like that. But I request you to kindly check. But this is the method by which you can do. And for you, we have a similar problem which you can solve, that is 13.5b. You can try to solve it yourself. Okay, so that would be, again you will get the feel for this. So 13.5b, please try it yourself. This is the way you can solve it. So the next question is that if the wave number of the j equals to 2 to 3 rotational transition of 1h 35cl considered as a rigid rotor is 63.56, what is the moment of inertia and the bond length? Okay, similar kind of problem, right? Where your rotational transition means that EJ is given. EJ is 63.56 centimeter inverse, right? So your uh, and 2 to 3. So your uh, so this is actually delta EJ, right? So your 2 to 3 delta E for J 3 to 2 is actually 2b into 2 plus 1, which is 6b centimeter inverse. So your b is actually 63.56 by 6 by 6, which is coming as 10.59. See, this is the typical order what I was trying to say, centimeter inverse. Okay. So if b is that, we know already from formula, b is your h 8 pi square IC. So what is going to be your moment of inertia? I is going to be h by 8 pi square b to c, 6.626 into 10 to the power minus 34. Again we directly write kg meter square centimeter inverse is the unit. 8 into 3.14 square into b value, what you got, 10.59 centimeter inverse. So velocity will write also in centimeter, 8 centimeter second inverse, which ultimately I'll write it here. So we'll cut these things, right? So we have kg meter square as the unit and centimeter cut here. So we get the moment as here I as, okay, 6.626 divided by 8 divided moment of inertia is coming as 2.64 into 10 to the power minus 45 kg meters. Okay, so this is the moment of inertia. What is the bond length? So we know I is equal to mu r square. So what is the mu for this molecule? 1 into 35 divided by 36 mu, and when we convert it to 35 by 36 into 1.66 into 10 to the power minus 27, you get 1.61 kg into 10 to the power minus 27 kg. Okay. And now mu we got, then what is r? R is root over of I by mu. So this is in kg meter square, this is in kg cut, so meter square will be there in the numerator, which will square root of which is meter. So you see the all the units should match. So what I am going to get is, I am getting is 1.28 into 10 to the power minus 9 meter, which is in picometer. It will be, or you can say 1.28 nanometer, or in terms of angstrom. In terms of angstrom, what it would be? 0. So it will be 12.8 angstrom. Into 10 to the power minus 10 meter, right? So 1.28. So this is the bond length. So I urge you to solve the 13.6b problem, the similar problem by yourself, so that you will get more familiar with the formulas, and with that we will go to the next kind of problem. We have these two problems, and one of the problem here, and this many problems. So we'll try to go as quickly as possible so that we can finish by 8. 13.7a, given that the spacing lines in microwave spectrum of 27 aluminium, 1 hydrogen is constant at 12.604 centimeter inverse. Calculate the moment of inertia and bond length of the molecule. So I will not go into deep of that, I will just discuss one thing, and the rest of is like the previous one. So as you can see, I tell you already that the gaps in the rotational spectrum, or the spacing in the rotational spectrum, is 2b, right? 2b centimeter inverse. So here the 2b is 12.604 centimeter inverse. As you can see, your b is rotational constant is 6.302 centimeter So you use the formula just what we saw earlier, that 8 pi square IC. So from here you will get the I, right? If you put all the values, get I, and then I is equal to mu r naught square, or r square you can say. From there you will be able to calculate the, not mu, right? Sorry, r. So to do that you need to calculate the mu, which is reduced mass, and from there we will be able to calculate this. So just like the previous question, try to solve it. And yes, did anyone join our program? Some notification came. I'm not sure. I hope someone has joined. No, no one. Okay, we'll go back to our discussion. So you will be able to solve this problem also. So spacing is given for the next problem is 1.033 centimeter inverse. See, the rotational constant is even lesser in case of this molecule. Why? If you check the reduced mass for the next molecule, ClF 35 into 9, that is higher than 27 aluminium 1H, right? So as the B value is increasing, that is what, so sorry, the reduced mass is increasing, that is why your B is decreasing, right? Okay, so we'll go to this problem. The rotational constant is given. Calculate the ICl bond length. So again, this is straightforward than the previous one, where your B value was given. B value is here given directly, 1.1142 centimeter inverse. See, here your compound is 127I 35Cl. See how much the mu is, very high. 127 into 35 by 127 into plus 35 AMU. I'll tell you the value in kg. Wait for a bit. This is 4.55 into 10 to the power minus 26 kg. This is the mu value. That is why your B value is even lesser. So let us calculate the bond length once. So mu is given. What else we require? So again, I will not go deep. So as you know that your moment of inertia I is mu r square obviously, and also it is h by 8 pi square b into c. You know your b value. From there you will be able to calculate moment of inertia, and when you get your moment of inertia, you put the value of your mu there, the reduced mass, and from there you will be able to calculate your calculate the ICL. Now by the same logic we will be able to solve the next problem. So I am going to the next slide. Okay. So the question is the rotational constant for this 12C 16O oxygen is 1.93127 centimeter inverse in ground electronic state and 1.3099 centimeter inverse in the excited triplet electronic state. Calculate the bond length of carbon monoxide in both ground and excited electronic state. So you already know your B is proportional to 1 by r square, right? So let me write it like in ground state divided by B in excited state. So that is going to be r square of the excited state, r square of the ground state. Okay. So this is how your thing is going to look at, and if I write it something differently, that your RE by RG will be BG by B to the power half, which is square root, and your excited state bond length will be Rg multiplied by this factor. We'll come to that. Before, let us calculate what is Rg. That is the your let me write it all the terms here. What is BG rotational constant ground state. B is rotational constant triplet state. What is Re? Re bond length at excited triplet state. Rg is bond length at ground state. So we know that Bg is h by 8 pi square C mu r square Rg. Rest of the factor is constant, right? So let us calculate what is the value. 6.626 into 10 to the power minus 34 kg meter. Kg meter square second inverse. Bg value is given, which is 1.93127 centimeter inverse divided by your 8 into 3.14 square, 3 into 10 to the power 8 centimeter second inverse into mu is, mu also you have to calculate. Mu is your 12 into 16 divided by 28 a mu, which is 1.14 into 10 to the power minus 26 kilograms. So I'll put that value here, 1.14 into 10 to the power minus 26 kilograms into your Rg square. G is going to be, so this kg gone, this second inverse gone, this centimeter into centimeter inverse is going to cut, so we are going to get 6.626 into minus 34 divided by 8 divided by 3.14 square divided by 3 divided by 10 to the power 8. This is the square of this. Square of all the calculation, I will get 1.13 into 10 to the power minus 9 meter, again, which is 103 picometers. Okay, 103 picometers. And what is the value last time we got? Or 1.28, which is going to be 1. I think I have made some mistake. Some calculation mistake or someone doing. Well, 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 3 divided by 10 to the power 8 divided by 1.14 divided by 10 to the power minus 26 divided by 1.93127. 1.13 these millimeters. This picometer, I think I have made some. some mistake somewhere or the other. I can't find it out. See, the main mistake I'm doing for so long is I have started from here. I told you, no, I'm thinking something is off, something is off. That is, I am taking this should be 10 to the power 10, not 8. So we are going to have 1.7075 centimeter. I told you, na, something is off. So I'll erase the mistakes. So I can't do it here. So I will just cut it like this. So this is also divided by 100. Let me write divided by 100, and this is also going to be 9. Now it falls onto that range, right? Okay. Now here also, see, the unit and these things go hand in hand, so we need to be very careful. So here I am dividing it with another, so it will be 47 something around. So I will just play around with the minus 34, and here it is 10 to the power minus 10, it will be minus 44. I will just check with the calculation again. 6 to 6 into 10 to the power 34 divided by 8 divided by 3.14 square divided by 10.59 divided by 3 divided by 10 to the power 10. So it is going to be 47. If it is going to be 47, then it is coming out to be is minus 1.28 into 10 to the meter, which is actually not these values but 128 picometer. Again, here you can put the values anyway. Here I have again done the mistake, so please don't make this mistake. This is very embarrassing actually. So we are going to get this as 10 and 113 picometer. So what about the excited state bond distance? It will be 113 picometer into 1.93127 divided by 1.3099, which is going to be 137 picometer. So see, your excited state bond length is greater than the ground state bond length. Okay, so and we are in the estimation that dipole moment is not changing. Okay, no, dipole moment will change, right? If R is enhancing, then your dipole moment will change. That is not a problem. Okay, so we are going to solve the next problem, and I have 15 minutes with us. We'll discuss some part this table of moment of inertia. So these questions, these two questions are equivalent questions, and we can solve any one of them and see what they are trying to say. So they are saying that determine the HC and CN bond lengths in HCN hydrogen cyanide from the rotational constant B of this particular 1H 12C 14N is 44.316 gigahertz, which is 10 to the power 9 hertz, and the deuterium with the deuterium one. So see what we have to do. So for this question we need to look at this particular table from the Atkins 13.1 moment of inertia. See, this is a triatomic linear molecule. So this is of the kind, this one. See, this is this kind of, sorry, this kind of molecule. I suppose this is your H, this is your C, and this is your N. If this is the case and this distance is R and this C, cyanide distance R dash, then see, this is Ma and this is Mb. Mass of hydrogen is Ma, mass of carbon is Mb, and mass of nitrogen is Mc. Then your moment of inertia, I hope you can see, but if you can't, I will write it. So your moment of inertia will be something like Ma R square plus Mc R dash square minus Ma R sorry minus Mc R dash square divided by M. So this M is the total mass. It is not the reduced mass. M is Ma plus Mb plus Mc. So I'll write. So see, for the first molecule, we will consider 1H 12C 14N. For this, the moment of inertia is I. Okay. So and bond length. Bond length are not going to change. So R and R dash. Bit R is between HC bond length R dash is CN bond, and so this is common, and for deuterium we have C14N, the moment of inertia, suppose this is going to be I dash. Why? Because your mu is going to be different, right? So mu means the or the masses are going to be different for this case. So let us write Im. The total mass is for, so we are currently doing for the first one. I into total mass is going to be instead of ma I will write mh, right? R square plus m nitrogen r dash square by, so I have to multiply with m also, this thing, m minus m hydrogen r minus m nitrogen r dash square, which will give me m mh r square plus m mn nitrogen r dash square minus m a square r square minus plus minus m n square r dash square plus 2mh mn r dash. Okay, so we will take common im equals to, im means I into multiplied by m. Okay, so we are going to take common, what we are going to take common, we are going to take m h and r common, so we get m r, so we are going to, sorry, the square common, then we are going to take, see what is remaining, if we take r square and mh, we are going to get minus mh, right, from these two, this and this, and from this and this we will get, if we take common mn r dash square, then we are going to get m minus mn, and what is remain, 2mh mn r dash. So we will actually divide it with mh. Okay, if we divide it with mh, what we are going to get, this is m carbon plus m nitrogen, right? This is m nitrogen r dash square, so this is m hydrogen plus m carbon, so this is 2mh mh I have, so there mh will come, here mh will be gone, so mn r dash, right? Similarly, from here what we are going to get, I dash, right, m dash, right, and mh, so here also you are going to get r square, the bond lengths are not going to change, the mass are not going to change, but mass of deuterium has changed, right? So now this is, so so this is also different, mh dash, this is also different, going to be, and inside this is the different one is there, plus mc plus 2mn r. Did you get it what I have done? So I have just similarly I have written for this, but I have changed the molecule, so the moment of inertia is changed, I to I dash, the total mass will change because the total mass will change, right, and mh is changed, m dash, so here nothing is changed, here m dash h I have taken, and here nothing has changed. So I'll just do what, I'll just take a so I'll go to the next page maybe. Where I'll do I dash m dash by m dash h minus subtract this from this. Let me see what I am going to get. So these terms which are common, which will go, the thing that is remaining, I will write it here, mn r dash, this is common. Now this is, for this is 1 plus mc by mh m dash h minus 1 minus mc by mc by mh, and that term is also common. So this is what we have right now. So we have 1 gone, mc is also common, so mn r dash mc 1 by m dash h minus 1 by mh, mass of h is not I. So what do we got here? Get here. Suppose I dash m dash mh minus I m dash mh, but we will get mn r dash mc, then we are going to get mh minus m dash h divided by mh mh, and this is going to cut. So what are the things we need to calculate? So we need to calculate the R and R dash. Okay. So this is Mn MC R dash. So what is R dash? Is I dash M dash MH minus I divided by M dash H divided by Mn MC MH minus M dash. Okay. See, I know this is going to be higher than this, so I will take a minus here and take a minus here. Okay. So I dash so rotational constants are given. I is equal to 8 sorry 8 8 pi square IC, right? Sorry, this is BC, right? B is given, so I know what is going to be the value. Let me calculate once. Let me calculate the other thing. 6.626 into 10 to the power minus 34 kg meter square second inverse 8 into 3.14 square into 3 into 10 to the power 10 meter second inverse into B, right? So I'll just calculate the other question. 6.626 into the power minus 34 divided by 8 divided by 3.14 square divided by 3 into 10 to the power 10, that is 2.8 into 10 to the power minus 46 kg second inverse 1 meter square by 1 centimeter inverse into B. B is different for two different things, right? 46.316 gigahertz. So for the first it is 44.316 gigahertz. 10 to the power 9 so B is 8 so this is in centimeter inverse. B centimeter inverse you need to multiply with the C. So this value actually given B into C. So this is centimeter inverse, centimeter second inverse. So BC. So let me tell you what the things are given. So I'll start from here. This is centimeter inverse. Okay. So if you multiply with C, then it becomes AC 8 pi square I C centimeter inverse, but C unit is in now suppose 3 into 10 to the power 10 centimeter second inverse. So maybe I'll erase it from here. See, now the unit has become arch. That is, so this can be a unit of, if I am writing it like this, might be a little difficult to understand, so I'll maybe I erase this part. I will write all the things again. So your I is whatever I have written, 2 into 10 to the power minus 46 kg meter square centimeter inverse into B. Now B is given 44.316 gigahertz, that is 44.316 into the power 9 hertz. So we will multiply it with the speed of light, divide it by the speed of light, 3 into 10 to the power 8, that is second inverse, Rg is second inverse, right? Is centimeter into second inverse. Now you will get your thing in our earlier, what we do, 4.316 divided 772 centimeter inverse. See, I have done the mistake again. Okay, 1.447. So I'll put this value here and I will get 1.4772, that is 1.89 into 10 to the power minus 46 kg meter square. What about I dash? That is 2.8 into 10 to the power minus 46 kg meter square centimeter inverse. This is V by I have B dash. B dash is 36.208. So I dash is centimeter into centimeter, that will go on, and I'm getting from 32 into 10 to the power minus 46 kg meter square. So I'll put this value is here. So minus I dash, which is 2.32 into 10 to the power minus 46 kg meter square into m dash is the total mass of this, which is m dash is 2 plus 12 2 plus 12 plus 14 mu which is 28 into 1.66 into 10 to the power minus 27. Actually, let me write it 28 into 1. mh is 1 and both amu square will be there, so I'll take common 1.66 into 10 to the power minus 27 square. Similarly, I will write the second part, which is 1.89 into 10 to the power minus 46 millimeter square. Into the next part is total m is 1 plus 12 plus 14, 27 mu into m dash is 2. See, here is the catch. M dash is 2. Now 1.66 into 10 to the power minus 27 square. So this is kilogram kg square kg square. Below I am going to get mn into mc, which is for 12 into 14, that is in kg square. Also in this term I am going to get 1.66 into 10 to the power minus 27 square, right? Because coming from both this, and then I am going to get 2 minus 1 into 1.66 into 10 to the power minus 27 kg. So from the above portions, this kg square is gone. This kg is also gone. This kg is also gone. So the thing I am left with is meter square r dash. Why it is coming in meter square? Did I made any mistake in some part? Yes, I have done. This is mn r dash square. I have mistakenly write it as, so this is square, right? Okay, no problem. Now I again go back to the red. So I am going to get r dash square is equals to, now I will calculate. here is 37.1. And in the minus 46 I have taken common. Below it will be 12 into 14. So this is 278.88 into 10 to the power minus 27. Okay, so your r dash square is 37.1 divided by 288, sorry, 278.88. One point 33 into 10 to the power minus 20 meters square, which in terms r dash is going to be 1.15 into 10 to the power minus 10 meter, and r dash is 115 picometer. Now what you can do, as you can see, these are two equations, equation 1 and equation 2. So you can put either the value of r dash here and you can get the value. So I'll write it here. Now you got your r dash value as 115 picometer. Now putting the value of r dash in either equation 1 or 2 will yield in r value. Try to do that and also try to solve for 13.9b using the same formula. See, it was a very lengthy one problem, but try to see what logic I have given and try to solve it by yourself. I know today we have exceeded our time. I will stop it here and let's hope we'll have a session uh, next week, and we'll try to learn some more thing about the vibrational spectroscopy, and if I am getting time I'll try to solve more numerical problems like this. So with that we'll stop it today, and